In today's chem activity, we're going to be looking at carboxylic acid derivatives and their reactions, particularly to prepare for chem activity 24B. Aldehydes and ketone chapters, we found the primary mode of reactivity for an aldehyde or ketone is for a nucleophile to attack the carbonyl carbon to give us a net addition product, like so. A different type of reactivity takes place when you have carboxylic acids and derivatives. Now, carboxylic acids, as you may recall, have a carbon atom with 3 bonds to oxygen. They're more highly oxidized than aldehydes or ketones. Other things that are in the same oxidation state include esters, acid chlorides, acid anhydrides, and amides. All of these have a carbonyl attached to another electronegative element, carbonyl with another electronegative element, carbonyl with another electronegative element, and all of these compounds are also, under the correct conditions, potentially have a leaving group. For example, the chloride can leave in an acid chloride. The whole red acetate group here can leave in the acid anhydride. The OH can leave generally with the help of another reagent or proton. Likewise, the OR in an ester can leave normally with protonation as a leaving group. And finally, the nitrogen reagent could potentially leave as a leaving group. All of these compounds can theoretically be interconverted into each other by doing a nucleophilic substitution reaction. For example, if we substituted this acetate group here for this chloride, it would allow us to convert an acid chloride into an acid anhydride. Likewise, if we use the whole acetate leaving group, an OH or water as a nucleophile, we could turn an anhydride into a carboxylic acid. We've already seen in the past quarter that we can interconvert carboxylic acids and esters. And finally, we can potentially convert any of these by losing those leaving groups into a nitrogen. In particular, acid chlorides are the most reactive of these groups, followed by anhydrides. Carboxylic acids and esters have a much stronger base, weaker leaving group, and react much more slowly, and the NH2 leaving group is the weakest leaving group of all. So it turns out that we can convert anything that is more reactive, such as the acid chloride, readily into any of the less reactive species. Likewise, anhydrides can readily be converted to acids, to esters, or to amides. However, it is much more difficult to convert a less reactive substrate like an acid, an ester, or an amide into a more reactive substrate such as an anhydride or an acid chloride. In the chem activity, we will be looking at the same types of reactivity. So let's quickly go over the 2 kinds of mechanisms that can occur when you have nucleophilic acyl substitution. This is distinctly different from the addition we saw for aldehydes and ketones. So let's look briefly at the mechanism for 2 different types of nucleophilic acyl substitution. First, when we have a more reactive acid group turning into a less reactive acid group, such as an acid chloride to an acid anhydride, we get a very simple nucleophilic substitution reaction. That is, the nucleophile, which in this case is an acetate ion, attacks the carbonyl carbon, and the lone pair of electrons moves on to the oxygen atom. So at the end of the first step, we have our net tetrahedral intermediate. Now, the tetrahedral intermediate is going to tend to eliminate the best leaving group, and in this case, the weakest base best leaving group is chloride. And in doing so, we end up in 2 steps creating our substitution product. First step, nucleophile comes in, forms a tetrahedral intermediate. Second step, the best leaving group leaves, reestablishing the first carbonyl, and in this case making our anhydride. Now, our second mechanism is one that takes place when you are trying to convert 2 things that are more closely related in energy, such as a carboxylic acid and an ester. In this case, the reaction will not occur unless you can make the OH or the OR into a better leaving group, and particularly you add a mineral acid such as sulfuric acid. To turn a carboxylic acid into an ester, you need to add an alcohol with the same number of carbon atoms as the R side of the ester. And to make an ester into a carboxylic acid, the reverse reaction, you will need to add water. This allows us to control the equilibrium by adding excess acid or alcohol on the left to move towards the right, or excess water on the right to move towards the left. Now this mechanism involves a few extra steps compared to the nucleophilic acyl substitution above. To start with, we will have to protonate, because we do not have a negatively charged nucleophile. And since the whole reaction is reversible, so is every mechanistic step. After we protonated our carbonyl, we have a superactive electrophile, and so our nucleophilic alcohol molecule can attack our carboxylic acid. Once the alcohol has attacked the carbonyl, we've made a tetrahedral intermediate, not unlike the tetrahedral intermediate we saw above, though a different protonated form of the same intermediate would have the positive charge on the oxygen on top. This makes the oxygen on top become a good leaving group, water, and when water leaves, taking its electrons with it, with the assistance of an adjacent pair of electrons, we find we get something that is very close to our product ester. In order to convert this last intermediate into the product ester, we need only lose another proton to a base in solution. Overall, if you follow the arrows around the outside, you go through a series of acid-base reactions along with the key nucleophilic addition to a carbonyl and then elimination of a leaving group that gives you your net substitution of OH to OR. Since it is a reversible reaction, each of these steps could be reversed to get you back to the beginning.